Hey, good morning, everybody. Today we're going to be going over day 2 of polar coordinates and really just practicing converting between rectangular and polar coordinates um, and seeing that we can also do this with the equations at the very end. But if you remember yesterday, polar coordinates are just when you have a coordinate written with the radius and the angle needed to get from the x-axis to that position. Where rectangular coordinates are just what we're going to call regular, just because we've been practicing with those for so much longer. Um, but really, it comes down to this. So an x coordinate is the same thing as r times cosine theta. Y is equal to r times sine theta. And that should make sense just because cosine theta is x on our unit circle, sine theta is our y value on our unit circle, and beyond that it just gets scaled. So if we wanted to reach this coordinate, maybe it's outside of the unit circle, cosine theta would get us to some position, so it should get us to basically here, this x and y coordinate if I do cosine theta, sine theta. And then to reach that, I just need to extend it from 1 to whatever r is. But that's the basis behind it. It's pretty simple going from polar to rectangular just because we do have this quick, simple formula. It's a little bit more to go the opposite direction. We'll get into that in a second. But nothing you can't handle, just it requires a little bit more work because it's not just simply plugging in and going. But you get the idea. So when we do this, we just need to plug, so we're converting to rectangular, so we want to change this into an x and y coordinate instead of r and theta. The x coordinate is going to be r times cosine pi over 6, and then y is going to be 6 times sine pi over 6. Cosine pi over 6 is root 3 over 2, so 6 times root 3 over 2 is going to be 3 root 3. So I'm going to write that right there. And then sine of pi over 6 is 1/2. 6 times 1/2 is 3. So these are the exact same coordinate, just written differently. It's important to know that they are exactly the same. Exactly the same. They're in the same position. They mean exactly the same thing, except for how you get there. One is moving along a rectangle. One is moving around in a circle with a certain radius. Only a difference. All right, -4 and negative pi over 4. Again, you're going to plug it into cosine and sine. -4 times cosine negative pi over 4. Cosine of negative pi over 4 is root 2 over 2 times -4 would be 2 negative 2 root 2. And then the y value is going to be the same idea. Sine of negative pi over 4 is negative root 2 over 2 times -4 is going to be positive 2 root 2. So we get negative 2 root 2. I don't know why I keep doing that. Negative 2 root 2, comma, positive 2 root 2. And again, they mean the exact same thing, just different directions to get to that coordinate. The nice part about this is you can use your calculator to check or do it for you, but if you hit second and then apps, it goes to your angle method or your angle features. We've been to this before when we were converting between degrees, minutes, seconds to decimal or decimal to degrees, minutes, seconds. But we're going to go scroll down to, I believe, I always forget which point to, so P to Rx. So this is polar to rectangular x coordinate. and then we'll repeat the process for number 8, which is polar to rectangular y-coordinate, basically. You're gonna hit enter or hit 7, and then you're gonna type in the coordinate. So 6, comma, pi over 6 for number 1 over 6, and kind of looks like garbage, but we'll see if that's correct. So 3 times root 3 was our x-coordinate. 3 root 3, and what happened there? Interesting. Okay, my note says that my answer is right. I'm going to check to see if this matters. Calculators are fun. Okay, let's check it again. Cross your fingers. Whew. Okay, so degrees matters. That's news to me, but that kind of makes sense. Pi over 6 is a pretty small number in degrees, but not a very small number within radians, so it should be shooting out pretty drastically, which makes sense. I don't know why the degrees that matters, because polar coordinates we don't really talk with degrees, but I'm going to stop struggling. Okay, so we're going to do the same thing again, but with the y-coordinate. We're in degrees, or we're in radians now, so it shouldn't mess up. Okay, so second apse, which is really angle, go down to 8, and then 6, comma, pi over 6. And if you remember, the comma's right there, so you do have this ability to type in commas. Pi over 6. And 3, which is what we got. Cool. I'm going to skip the second one. You can try that one on your own, but basically the same process. Should come out to be the same thing. You can do this. Hey, look at that. Degrees. Pff, your teacher sometimes. Pff, I tell you. So make sure you switch it into degrees. That way it'll give you the correct answer. Clear. And entry, and we're going to change that to -3, comma, 182. Oh, sorry, -3.1. Now, comma, 182. Parenthesis, enter. And we have 3.098. Sure. And then from there, we are going to do the same thing. Second entry, and I am going to change that. Almost there, got it. I'm going to change that into, again, the P to RY. If you wanted to go the other direction, it's okay, good. Whew. All right, and 0.108 probably means nothing to you, but there's how you do it. All right, so converting from polar to rectangular isn't too interesting unless your teacher keeps messing up. Then it gets a little interesting, I think. But it starts to get a little more complicated whenever you have to go from rectangular to polar, just because you have a few more complicated calculations. First being the radius. So if you remember, we can always make right triangles with these. So 2, -2 would be down here if this was 0, 0. So this is 2, this is -2. R is just the hypotenuse. So basically you're finding the hypotenuse of this right triangle. To find r, you're going to use Pythagorean theorem. So 2 squared plus negative 2 squared is equal to r squared. So r is the square root of this. I would just stick with the positive. Technically, you could go with negatives, but it screws this up a little bit, or it just makes you have to think a little bit more with it. So up to you, but just make sure you're going to be landing in the correct spot. All right, so this is 4 plus 4, so this is root 8. If you want to get technical, it's 2 root 2. And then to find the angle, you're going to use inverse tangent. So this is going to be in quadrant 4, which quadrant 4 and quadrant 1 are easy because you don't have to do anything. You just have to take inverse tan of those things. But you also can figure this out without using your calculator. These are the same length, so the same absolute value. And so that means that we have an isosceles triangle. When we have this is a root of pi over 4. So this should be negative pi over 4, or you could go the other direction and go 7 pi over 4. Doesn't really matter. If you type it in your calculator, it would give you the negative pi over 4, so I'm going to go with that. 4. Okay. It gets a little trickier when you have quadrant 2 or 3, but basically you just have to add pi to whatever your tangent answer is. Or you could just make r negative, and that would flip it over. Either way should work. Always check though, just in case. All right, -1, negative root 3. It's going to be about right here. And if you divided everything by 2, it might look a little bit more familiar. These are forms of pi over 3. So this should be, the angle should be inverse tan of root 3 over 1, or just root 3. And this is going to be pi over 3. But it's in quadrant 3. We know that because this coordinate's there. So we need to add pi to this. So 4 pi over 3 is our angle. And we want to, squeezing everything in here. I'm going to take that out, draw just the triangle. -1, negative root 3. 1 squared, root 3 squared, that's going to be 4. Square root of that is 2. Our radius is 2. You could also just figure out how to scale this -1/2 to get to -1. You have to do that by multiplying by 2. But either way, 2 is r. So 2, 4 pi over 3. Again, another route. You could just take inverse tan, deal with pi over 3, which would be over here. And then if you made it a negative radius, it'd be over here. But a few ways to go about it. I'll let you check on your grapher. It's basically the same process, but just using a different button. This is going from rectangular to polar, so just find those options. 5 and 6 should be just above the ones that we just used. All right, transforming an equation. Now we're getting a little trickier. Transforming an equation from polar coordinates to rectangular coordinates. Basically, when we have equations using theta and r versus equations with x and y. And all we need to know is that y equals r sine theta, x equals r cosine theta. Using this information, we should be able to convert an equation that's using polar coordinates, polar variables, and turn it into rectangular variables. And then we're going to identify the type of graph. So you can graph these, and we will be graphing these, but it doesn't. It's a little difficult to see it from here, just because we're not used to plugging in things like this. But if we can convert it into x or y type of equations, then it should be a little simpler. All right, so we're gonna dig in. To do this, I would multiply both sides by r. So this will feel a little bit like establishing an identity, where you kind of have to produce your own ideas. You have to put them into the equation just to get to things that you recognize. Right now we're really close to r sine of theta. I can't just simply move this over, because by moving that over I have to divide, and that's not going to be helpful when I want r times sine instead of sine divided by r. So instead I'm going to multiply both sides by r. Okay? Now we need one more thing. The fact that r squared is equal to x squared plus y squared. We have r squared and we have r sine theta. Both things we can relate to x and y. So I'm going to change this to y. I'm going to change this into x squared plus y squared. So x squared plus y squared equals 4y. Now, you might not be able to recognize it from here, but it wants us to identify the type of graph. And you guessed it, we're going to get into this later, but we have conic sections, which there are 4 different types of conics that we'll talk about. 3 that we'll talk about at greater lengths because they're more interesting. But this is a type of conic section. Now, which kind of conic section depends on our next steps. So if you can't recognize it from here, we're going to keep going. I'm going to start off by getting everything to one side, and you might wonder why that is. It's because I have an idea of what it should be. So from here, we have to complete the square. X squared is already completed, but y squared minus 4y isn't. If you remember, completing the square, it means you have to take half of this, or half of your linear variable, and square that, and then add that to both sides. So we're going to take half of negative 4, which is negative 2. We're going to square it and add that number to both sides. So negative 2 squared is 4. I'm adding 4 to both sides. Now we have a complete square with this here. Again, x squared is already completed. If I factor y squared minus 4y plus 4, it should be y minus 2 squared. So completed square, and that's 4. This should look familiar now. If you got it from here, that's fine, but really you should be able to get to this point and practice this because we will be getting into this. But x squared, y minus 2 squared, this is a circle. So it's a circle with a center at 0, positive 2, and then a radius of 2, square root of that. Okay? Which is kind of cool. The fact that we have this thing, which looks very simple, and it turns into a more complicated version of x and y, but circles look like this, and that's pretty cool for me at least, because it's I wouldn't expect that coming into this without any prior knowledge. So we will be practicing how to graph these without converting to rectangular coordinates or rectangular equations, but it feels a little complicated because we're just not used to it, but we'll get into that. All right, transform the equation 4xy equals 9 and we want to convert basically, so we're going to convert it into polar coordinates, and then just like we normally solve for y, we're going to solve for r here. Most of the polar coordinates are solved for r. Doesn't have to be, just like doesn't have to be solved for y in these cases, but most of the time you're going to solve for r in these questions. All right, so we're going to just plug these in. So x is r cosine theta, y is r sine theta. So r, or x, and then our y, and then simplify, solve for r. If you multiply this out, we get r squared 4 cosine theta sine theta. You are then going to divide by r cosine sine, sorry, just 4 cosine sine, which is that bad boy. And then we're going to take the square root of this, plus or minus . Okay. Now this does, wait a second. You can change this a little bit. So it does simplify more, and I'm going to go, so this is technically correct. I wouldn't care too much if you went with this versus what I'm about to show you. But I do want to cover it, so let's make sure we get that down. Before I did that, so parallel solve over here. R squared. This is the same thing as 2 times 2 cosine sine, which feels a little weird, but our double angle formula for sine is 2 cosine sine. So I'm going to change that into sine of 2 theta, which just makes it look simpler. That's the only reason that this is being done this way. So then you could divide by both those things, and you get that r squared is equal to 9 over 2 sine 2 theta, and then you're going to take the square root of that. So the reason that this is nice is it is a little bit simpler. The reason that this is nice is that you don't have 2 theta, so you don't have to deal with the double angle. But it kind of just depends on preference. You technically could solve, or you could simplify this a little bit more, so it'd be 3 over root 2 sine 2 theta. That's not a rationalized denominator, but that looks terrible, so I wouldn't want to do that. But yeah, okay, I've rambled on enough, struggled enough. So this is the second part of polar coordinates. We're going to keep going into it, and we're going to start graphing these in later lessons, so stick around. But until next time.